I'm Adienex Fernandez, and I'm going to be talking about some algebraic techniques that are used in graph theory. So I'm going to be talking about graphs, matrices, and ideals. And first, we need some graph theory. So here we have an example of a graph that we're going to refer to as G. And usually we think of graphs as like graphing a function, but for us, a graph is going to be a set of vertices and a set of edges. So our set of vertices is vertex 1, 2, 3, and 4. Our set of edges are the lines connecting the vertices. So we have 1 and 3, 1 and 4, 2 and 4, and 3 and 4. Two vertices are adjacent if there's an edge connecting them. So we have that vertex 1 and 3 are adjacent, 1 and 4 are adjacent, etc. The neighborhood of a vertex is the set of vertices that are adjacent to it. So the neighborhood of vertex 2 is vertex 4. While if we look at the neighborhood of vertex 4, then that's vertex 3, 1, and 2. A simple graph is a graph that has no loops or parallel edges. A loop is an edge from a vertex to itself, so we can see that in the upper corner here. Parallel edges are multiple edges between two vertices, and we can see that on the left side. So this is not a simple graph. So we also need to know the degree of a vertex. The degree is the number of edges that are incident to the vertex. And because this is a simple graph, that's also the number of vertices that are adjacent to it. The degree of vertex 1, we can see that that's 2. The degree of vertex 2 is 1. The degree of vertex 3 is 2. And the degree of vertex 4 is 3. And then the total degree is the sum of the degrees, which is 8. Then our last graph theory definition is a walk, which is a sequence of vertices that are connected by edges. So we can see that there's a walk from vertex 1 to vertex 2 of length 3. Then we can move on to some algebraic techniques. The first one that I'm going to talk about is matrices. So I'm going to focus on the adjacency matrix. For a graph with n vertices, this matrix is going to have n rows and n columns. And an entry would have a 1 if there's an edge between the vertices and a 0 if there isn't. So for G, we get this matrix. We see that the diagonal is zeros because there are no loops. Entry 2, 1. For example, is also a 0 because there's no edge between vertices 2 and 1. And entry 3, 1 is a 1 because there is an edge between vertices 1 and 3. Okay, we notice that this matrix is also symmetric along the diagonal because if there's an edge between 1 and 3, then that's going to result in a 1 in the 3, 1 entry and in the 1, 3 entry. So the main result of the adjacency matrix is that the entries of a to the k give you the number of walks between vertices that use exactly k edges. So for example, we have a squared. We multiply a by itself. Then the 2, 1 entry, which is highlighted here, of a squared is given by the dot product of the second row of A times the first column of A. And this dot product is basically scanning the neighborhood of vertex 2 and the neighborhood of vertex 1 and seeing if they have anything in common. So in this case, they have vertex 4 in common, which tells us that there is a walk of length 2 from vertex 2 to vertex 1 that goes through vertex 4. So this entry in the matrix corresponds to this walk in the graph. So there are similar matrices for directed graphs. A directed graph is a graph where the edges, which are now called arcs, have a direction associated with them. And we can see the direction by the arrows. Directed graphs also have out degrees and in degrees. The out degree is the number of arcs going out from a vertex, and the in degree is the number of arcs coming into a vertex. So for example, vertex 3 has an out degree of 1 because there's an arc going out to 4, but it also has an in degree of 1 because there's an arc coming in from 1. So the adjacency matrix of a directed graph has ones if there's an arc going out and zeros everywhere else, but we modified the matrix so that it would have ones, zeros, and negative ones to distinguish between the direction. So the ij entry of our new matrix would have a 0 if there's no arc between vertex I and vertex j. It would have a 1 if there's an arc going out from vertex j to vertex I, and it would have a -1 if there's an arc coming into vertex j from vertex I. So we have the directed matrix for our graph here. We see that all the entries that were zeros and A are still zeros. And we notice that entry 3, 1 is a 1 because there's an arc going out from 1 to 3, while entry 1, 3 becomes a -1 because there's an arc coming into 3 from 1. So we can see that this matrix is very similar to the adjacency matrix, but not symmetric because half of the ones turned it into negative ones. The result of this matrix comes from multiplying the adjacency matrix times the directed matrix. And the diagonal of the product gives us the total degrees of each vertex. So we can see the product here. We can see the total degree of vertex 1 is the out degree minus the in degree. So 2 minus 0 is 2. For vertex 2 is 1 minus 0 is 1. Vertex 3 is 1 minus 1, so it's 0. And vertex 4 is 0 minus 3, so it's -3. So we can see that the total degrees match with the graph and it matches with the diagonal of the matrix. The second algebraic tool that I want to talk about is ideals. And the first one is the edge ideal. So the edge ideal is generated by the edges of a graph. So for our graph, we see that we have v1 times v3, v1 times v4, v2 times v4, and v3 times v4. The cover ideal is given by the intersection of the pairs of vertices that form edges. So this is the cover ideal for our graph. We see that we have v1, comma v3, v1, comma v4, v2, comma v4, and v3, comma v4 for all of the edges. And we can also see that the generator v1 times v3 in the edge ideal turned into v1 comma v3 in the cover ideal. And that tells us that the edge ideal is the Alexander dual of the cover ideal, where the Alexander dual is an operation that's denoted by the V symbol, and that's taking an ideal and going from the generators of that ideal to its components. So a big part of my work has been reading and understanding a paper about associated primes and odd holes in a graph. Theorem 4.2 in that paper tells us that G has no odd induced cycle of length greater than or equal to 3 if and only if the saturation of J squared with respect to L sub 3 is equal to J squared. So the irreducible decomposition of J squared is given by theorem 3.2 from that paper. We have x1 squared comma x3 intersect x1 comma x3 squared, and we're doing that for every edge in G. Then we also have this x1 squared, x3 squared, x4 squared piece at the end. And we get that because the only odd cycle in our graph is the one formed by vertices 1, 3, and 4. So we define L sub 3 to be the product of all the combinations that are using 3 vertices. So we get x1 plus x2 plus x3 times x1, x3, x4 times x1, x2, x4 times x2, x3, x4. And lemma 4.1 gives us a method for computing the saturation of J squared with respect to L sub 3, which is shown here. By looking at L3, we can see that every term in that product is going to be made up of x1s, x2s, x3s, and x4s. So because there is no term that is only made up of x2s, we know that L3 is going to be in the ideal generated by x1 squared, x3 squared, x4 squared. And because L3 is in there, we have that piece is missing from the intersection. So we get that the saturation of J squared is not equal to J squared. So since the saturation of J squared is not equal to J squared, the theorem tells us that there exists at least one odd-induced cycle of length greater than or equal to 3. And we can see that this is obviously true because there is an odd cycle of length 3 made by the vertices 1, 3, and 4. So these are just some examples of the many algebraic techniques that are present in graph theory. We can see that performing operations on the matrices and on the ideals gives us different results in the graphs. Like it tells us the number of walks, or it tells us about the degrees, or tells us about whether there are cycles or not. So there's a lot of things that you can do with algebra that are going to tell you things about graphs. So we can see that studying algebra is really useful in the study of graph theory.